going to prove the standard log rules or ln rules using integration. Note that if you have the integral of dt over t, this is just ln over t. So what I can say is that ln of x, I'm replacing absolute value of t with x, is equal to the integral of dt over t. Now remember, this is ln of t from 1 to x. And we're going to assume that x is 0. So, okay, so it's ln of t. And I evaluate it from 1 to x. But they're both positive. X and 1 are both positive. So I do not need to include the absolute value bars. And ln of 1 is 0. And ln of x minus 0 is ln of x. So this integral is actually equal to ln of x. Whoops. If we go from 1 to x. So that's basically a definition. This is ln of x. So now, if we had, instead of x, we had ln of a, this is equal to the integral of dt over t from 1 to a. But I guess what I really meant to write, if I need to erase all of that, is that ln of ab is the integral from 1 to ab of dt over t. And ultimately, I want to show that that's ln of a plus ln of b. So I looked at this carefully. I have this, I have 1. Well, if I went to a, then that's ln of a. Got that. So I'll do that. But then I have to pick up at a and then go to ab. Then I cross my fingers that this is just ln of b. So I make this substitution change. I let t equal au. So then dt is a du. And when t is a, if this is a, then that must be a times 1. That is, u is 1. And if t is ab, then ab is equal to a times b. That is, u must be b. And let's see what happens with this substitution. So I have the first integral, which is ln of a, plus the second integral, where I made a u substitution. When t is a, u is 1, and when t is ab, u is b. And I have dt, which is a du, over t, which is a u. And this cancels out. And then I have it. The first term is ln of a plus, this is just ln of b. And we prove the first law. Now, let us try the second law. We want to prove that ln of a over b is ln of a minus ln of b. The proof is going to be similar. So we're going to start off with this. So let me write that. So ln of a over b, this is equal to the integral from 1 to a over b of dt over t. And like always, instead of going from 1 to a over b, I want to go from 1 to a. This gives me ln of a, which is what I want, plus the integral from 1, pick up at a, and then go to a over b. And this is dt over t. So somehow I want to show that that is negative ln of b. So I'll let t equal to a over u. So when t is the lower limit, then u must be 1. After all, a divided by 1 is a. And if t is a over b, then u must be b, because a divided by b is a over b. So if t is equal to a over b, then u is b. And this here is the same as au to the negative 1. So then du will be negative a, u to the negative 2 du. I meant to say dt equals that. That is, dt is negative a over u squared du. Okay, so first integral here is ln of a plus the integral. Now we're going to go into the u language. When t is a, u is 1. And when t is a over b, u is b. And dt, well, that's negative a over u squared du divided by t, which is a over u. The integral of that whole mess. Now, this is equal to ln of a. This minus sign is going to come out in front. The integral from 1 to b. The a's cancel. And 1 over u squared divided by 1 over u. Well, here's the du. And 1 over u squared divided by 1 over u is 1 over u. So then I get the ln of a minus the ln of b, just like we wanted. Last theorem. Natural log of a to the r, as long as a is positive, is r times ln of a. A must be positive. Okay, and the proof is going to be very similar. Ln of a to the r is the integral from 1 to a to the r of dt over t. But this time we're not going to break off an ln of a, only because the result doesn't have ln of a. It has r times ln of a. So I'm going to say let t equal u to the r. So then dt will be r times u to the r minus 1 du. And when t is 1, we'll find u. And when t is a to the r, we'll find u. Well, if t is 1, what to the r is 1? 1 to the r is 1. So u is also 1. And when t is a to the r, just let u be a, and you'll get a to the r. U is a. So what we get is the integral. Instead of 1 to a to the r, we go between 1 and a. Okay. And dt is, whatever it is ru to the r minus 1 du. divided by t, which is a to the r, u to the r, excuse me. So this r having nothing to do with u can come out in front. So we have r, integral from 1 to the a. And if you have u r to the negative 1 over u to the r du, well, the du stays on top. This here has one more r than the top. That is, you're going to have one r left in the one u. Okay, let me say this correctly. I apologize. This here has one less u than this has. This is u times itself r times. This is u times itself one less time. So you have u times itself a certain number of times, and the bottom you have that number of times, and then one more, because this power is one more than that power. This cancels out to 1, that cancels out to 1, all of those canceled out to 1. The last one cancels out to 1, but you still have a u in the bottom. You get 1 over u, or du over u. So you get du over u. But let me get rid of some of my side work. Well, that's r, and this integral we know. It is ln of a. So I did prove that if you start with this, you end up with that, which is exactly what I was asked to prove. And this completes the video on how to prove the ln theorems using natural logs.